Now we're going to bounce back to the science. We're going to have Annie Bauer come up, and she's going to tell us about the early stages of Earth and how it came from something molten, hot, and then starting to cool down to make it a habitable planet. So we're going to hear from Annie Bauer in 2 minutes about the habitable Earth and how it became livable for us. And we can find out from the oldest rocks how they cooled. And I know you've been wondering, small child, did Earth ever have a goth phase? We'll find out. Please welcome to the stage, Annie Bauer.
Oh, can I get this?
Oh, sure, yeah.
Hi, everyone. Today I want to tell you about my favorite part of Earth history, which is the first billion years. And I think this is a really important part of Earth history because it's when the Earth transitioned from its infant state, so this big molten squishy ball of material that's relatively homogeneous, to the one that we're more familiar with. And during this first billion years is when this process kicked off. So you started to form the core, the mantle, the crust, the oceans, and the atmosphere. And so that's part of what made Earth a habitable planet. When you were walking into the Majestic today, you probably weren't thinking about all the special traits that make the Earth a habitable place for you. But let's not leave those unnoticed, right? So the Earth has an oxygen-rich atmosphere, and it did not for most of its history. We also have continents. So there weren't continents on the earliest part of Earth history, and the continental crust reservoir has grown over time. There weren't plants. Plants didn't evolve until just over 400 million years ago. And there wasn't surface water. And so today we're going to talk about continents and surface water specifically. This is a drawing of what the scientific community thought for a long time the earliest part of Earth history looked like. This period 4.5 to 4 billion years ago is called the Hadean. It's trying to evoke Hades or hell-like conditions on the planet. So you can see there's a magma ocean. There's some noxious-looking gases in the atmosphere. There's lots of material raining down and hitting the Earth. And what you're probably staring at is the moon, which is very close to the Earth and glowing red hot. So you probably know that dinosaurs went extinct when an asteroid hit the Earth. But what you might not know is that the moon formed in a similarly or more extremely violent manner. Here's an artist's illustration of a Mars-sized impactor smashing into the Earth, causing everything to melt and homogenize and then pulling off and then getting locked into orbit around the Earth. We think this is how the moon formed. So the early part of Earth history was very violent, as I said. On the right-hand side here, I'm showing some plots of models, trying to show what the Earth's surface may have looked like early in Earth history. So if you imagine the Earth like a beach ball, and you take a pin and you pop it and then you stretch it out like this, that's what these are showing. And what we've done is we've looked at the moon. We don't have impact craters preserved on the early part of Earth's history because there's erosion and plate tectonics, which are really efficient at destroying the Earth's surface and sweeping material away and recycling it back down into the Earth. So by looking at the cratering record on the moon, we can extrapolate what it looked like on the Earth. So in the top one, you can see at 4.4 billion years ago, in the first 150-ish million years of Earth history, the Earth is littered with impacts. The entire surface is literally covered. These are color-coded by their respective age. So the one below that at 3.8 billion, you can see that the impact rate is curtailing, but that there's still quite a bit of impacts on the Earth's surface. And I'm showing this to point out that if life originated during this time, it might have been sterilized, right? Or it would have been really hard to live at Earth's surface during this time and also to preserve fossils from that era. So the questions that we're going to think about today are, when were the first continents? When did plate tectonics start? And when did we get oceans on Earth? And we're going to do this in really rapid fire manner today. So first we're going to talk about the continents. I'm showing here a map using the color brown to show you rocks that are at least 2.5 billion years old, so from the first 2 billion years of Earth history. You can see this is sparsely distributed across the Earth. It's about 6% of the surface area of the rocks on the surface of the Earth today. And we don't know if that's all there ever was, or if there was a lot more continental crust and it was selectively destroyed over time. But what we're going to talk about today are some of the oldest vestiges of crust. So the oldest thing that you can date on Earth that formed on the Earth is 4.37 billion years old. It's a mineral fragment that was found in a sediment. So it's a mineral zircon that was originally crystallized in a granite and then got broken out of that granite and sedimented later into something else. The other thing that you can look at are the oldest intact rocks. So these are rocks in the Acast and Gneiss complex in the Northwest Territories in Canada. And they're an intact chemical package, although they have been metamorphosed, and I'll show you what those look like in a minute. If you go work on these rocks, it's kind of a remote location, so you end up camping on this island that you see pictured here. It looks like Snoopy from above. And if you squint, you can see little orange tents. You're gonna camp on that island because it's harder for the bears to swim out to you. It's not a joke. But I like this picture because it was taken from a helicopter, and from this vantage point, you can actually see several places where there are 4 billion-year-old rocks. And so there's a really rich magmatic record there of over 1 billion years, and it is helpful for people like me who want to try to understand if plate tectonics was operating on the earliest Earth. So we can look at the chemistry of the rocks and try to work that back out. Our problem is a little bit complicated by the fact that these rocks have been metamorphosed. So you can see me standing with another scientist here on an outcrop of these rocks. They're highly banded because they've been strained. They were deep in the crust. They had a lot of pressure and temperature applied to them, and so the different minerals segregated out into bands. So if we can work back through all that metamorphism and look at their original chemistry, then we can start to think about plate tectonics. So now we're going to talk about when plate tectonics started on Earth. This is a very contentious question in our field. And the reason that we care about plate tectonics is because that's how we've made continents over time. Plate tectonics is the primary mechanism for forming continental crust. It's also the primary mechanism for recycling things back into the Earth, and so it's really important for the evolution of our atmosphere and our oceans too. You know a lot about plate tectonics already, even if you think you didn't, because in middle school you probably did the exercise where you cut all the continents out from a map and you can fit them back together like a jigsaw. So here is that supercontinent. It's called Pangaea. This is what it looked like 240 million years ago. You can see North America and Africa and South America all smushed together. And if you think about unzipping the ocean, the Atlantic Ocean basin, and pushing everything back together, you can keep doing that back through Earth history and saying, what if I unrecycle all the oceans that have been made? And as you project back billions of years, there are multiple of these supercontinents. So what we've been able to figure out with the chemistry of some of the oldest rocks in the world is that there might actually be multiple stages of tectonics on Earth. So when the Earth first formed in the Hadean, there wasn't plate tectonics. There's something that we call stagnant lid tectonics, where there's vertical movement of material to recycle into the Earth. It's basically things dripping off that are more dense and things that are floating up that are less dense, and that's about it for exchange with the deep Earth. If we come over to the Earth today, we have plate tectonics where we can recycle things all the way down to the core mantle boundary. And we have things like volatiles, like water, that are easily recycled through volcanic systems. But what we've been proposing is that there's some intermediate stage called mobile lid tectonics, because we had to come up with another name for it, which is kind of in between these two stages. And what we've been able to see from rocks at Acasta and other places is that there's a big transition on Earth around 3.8 to 3.6 billion years ago. The final question that we're going to tackle is, when were the first oceans on Earth? And this is a cool one to talk about in Madison, because this was actually first figured out in a laboratory just down the road from where we are right now. So this is a secondary ion mass spectrometer in a facility in the Department of Geoscience. And the group there looked at the oxygen isotope composition of some of these detrital minerals, and they were able to infer the existence of oceans on the Earth, which is a wild thing to think about. They're looking at microscopic amounts of material that you can't see with your naked eye, and they are inferring the presence of oceans on the entire Earth. I'm going to show you a little bit about how that works today. So what they did is they went to southwestern Australia, and they found some metamorphosed sediments there that were 3 billion years old. In these sediments, they found a lot of these detrital minerals that were chewed up out of former rocks that are older, all the way back to 4.37 billion years ago. These oldest ones are this mineral called zircon. And this picture of a zircon here is like if I took an onion and I sliced it in half and I polished it. So we're looking at all the different growth bands around it as it incrementally grew in a magma. This zircon's really small. They can actually subsample it to about the 10th of a width of one of your hairs. And the zircon itself is about the size of Lincoln's eye on a penny. So a really small amount of material that we're working with. And that's why you need that fancy mass spectrometer that I showed. What's cool about zircon is that when it forms, it takes up a bunch of uranium in its structure. And you probably know that uranium is radioactive. So that uranium decays over time to a stable daughter product of lead. And we can go to the zircon and we can take all the lead out of it and we can look at the ratios of those different isotopes of lead and we can work back out in age. So this one above me here is the 4.37 billion year old zircon. It's received a lot of attention, not only because it's 4.37 billion years old, but also because Beyonce wore a blue zircon dress to one of her performances. This was a very exciting day for geologists, as you can imagine. She subsequently deleted the tweet, but everyone had taken a screenshot already. Okay, so here's the part where I show you data. I have to show you data. So from this zircon and all the other ones that are younger, I'm showing a plot from 4.4 billion years ago to 3.8 billion years ago. On the y-axis, I'm looking at the relative amount of oxygen 18 to 16 in these zircons. And what I want to tell you, and I have this at the bottom of the slide, is that if I have a higher ratio of oxygen 18 to 16, we see that on the surface of the Earth today. Colder temperatures like we have at the surface of the Earth and the presence of water can enable us to do that. If you go down below us in the mantle, we see values more like these green values where they don't get as high. If you look at the zircon record above me, starting around 4.3 to 4.2 billion years ago, they punch up into this blue region. And so that is the evidence that we have from something you can't see with your naked eye, that we have oceans on the Earth by about 4.3 billion years ago. So the emerging picture of the Hadean period on Earth history actually looks like this. It's a little bit more habitable and clement looking than the one I showed you before, right? There's water at the surface of the Earth, and there are continents. So we have multiple types of environments that are conducive to the origination of life. That's all I have for today, but if you come find me at the end, I have a meteorite sample and a sample of the acastinice I'd be happy to let you hold. Thank you.
Thank you, Annie.